The task is to replicate the world in a program with every little detail. The program should include every little detail, from every simple thing up to things as complicated as life. And we want the program to also be as scalable as we want, meaning that it should always be possible to build bigger things as a construction of smaller things. We want to be able to specify the behavior and the properties of different things specific to them. And we also want to be able to define certain features for an entire group of things. Everything in that program must be able to take care of itself, just like the real world. So they should be able to construct themselves, behave themselves, and destruct themselves with minimum supervision. And they should do it correctly every single time. And it goes without saying, but we want this huge program to work correctly and be very, very stable. We absolutely want no bugs, as they can literally cost people's lives. The question is, what would you do to organize the code of a program of this scale and be able to maintain it? Is there any other way than mirroring the exact world? Well, that's exactly what object-oriented programming does. Welcome to episode 1 of 5 of Object-Oriented Programming series. Let's get started. It all started in the late 1950s. Computers were getting stronger, it was harder to write good software for them. As a result, the softwares were very unstable, and pretty much everything with software on it crashed many times. And in many cases, these instabilities of software resulted in extreme disasters. Just to give you an example, the bug in the Mariner 1 spacecraft costed about $18 million at the time, which is about $169 million in today's world. The software projects were incredibly huge, and it was impossible to organize them in a way that would result in no unseeable errors. So there were always errors that nobody could see in big software projects that resulted in terrible disasters. And it was at about this time that software engineers and computer scientists started thinking about how to organize the code rather than how to create the program itself. And they came up with object-oriented programming. A programming paradigm in which every software mirrors the real world and is therefore easily scalable and maintainable. So the question they started asking themselves was, what is the world made of? What is being made of? What is being? What is the essence? And the answer was kept very, very simple. The world is created out of objects. Everything is an object. It might be created out of smaller objects, but it's still an object. Every object has certain properties and behaviors. The food we eat, the cars we drive, and the lives we live are all objects. Every morning, an object called the sun goes up, and later that day it goes down, and another object called the moon goes up. As an example, let's take a look at these bubbles. They're also objects, right? They have their own properties, like their size, their volume, their shape, and them being see-through. And they also have behaviors, like the way they're created, or rather constructed, the change of their shape as a known, the way they move in the free space, and the way they blow up, or rather destruct as they hit other dry objects, like a grass. Alright, we've understood how to look at the world in an object-oriented manner. Now let's go further and see how it's done in object-oriented programming. The keyword in object-oriented programming is class. We use it to define a family of objects. So we use class to define what properties and behaviors an object has, and we specify the exact value of those properties when we create an object of that class. Instances are mostly stored in a variable with the type of the class they're storing. For example, you say bubble1 is equal to a new bubble, and that bubble1 variable is storing a bubble in itself. Damn it, I said bubbles too many times. The properties of classes are either primitive data types that the programming languages gives you, or they're instances of other classes that you've created before. The behaviors are just a bunch of functions that have access to those properties of the class. We call those methods, just to not mix them up with the regular functions. A very important characteristic of classes is inheritance in object-oriented programming languages, meaning that the classes can inherit properties and behaviors from each other. You can use this whenever you need it in actual inheritance, or you can also use it to achieve abstraction or encapsulation, Together with polymorphism, they make the 4 fundamental rules of object-oriented programming. Let me show you what inheritance means. Take this flower as an object, for example. Some of its properties could be its genus, stored in a string, for example, its color, coded in RGB, and the number of its petals as an integer. Its behaviors could be growing, photosynthesis, and putting that aromatic compound in the air for that incredible smell. Now this flower you're looking at right now is an instance of its class. Here's another one with other property values, and there's one more. This class of flower inherits from the abstract class flower, just like all of these other flowers you see here. The abstract class flower specifies some common properties of all flowers, and it inherits itself from the more abstract class plant, for example. And some other children of the class plant could be trees, and they could have some extra other properties, and their own subclasses and instances with even more specific properties. So it's all ordered in a hierarchical manner. Get what I mean? It's all in looking at objects in a hierarchical manner and ordering them the way the nature has ordered them, and it works. So you could imagine, this type of programming is extremely versatile and could literally replicate the world. And that's why it's the #1 paradigm for huge software projects. Examples that use it are Photoshop and every single video game that you play these days, like Red Dead Redemption 2 with that insane amount of detail that it has. So everything you see in that game, the horses, the grasses, the characters, their movement, everything, it's all object oriented, okay? Those things are objects, and the things they do are their behaviors. Their properties are the way you see them on the screen. And that's pretty much the philosophy of object-oriented programming. Let me know in the comments down below what could be properties and behaviors of this little cute dog as an object, and what could be a hierarchy of classes in which you would replicate this. It's Algoritmi, and this was episode 1 out of 5 of the object-oriented programming series. I hope you enjoyed this video. Give it a like if you did, and stay tuned for more. I'm out.